Welcome to Nanda Academy. This is Dr. S. Nandagopalan. I'm going to explain about the candidate keys and how to find these candidate keys for any given relation. Or let's take. Also, you are given some attributes. So the idea of this particular video clip is to make sure that the viewers can easily understand in order to find the candidate keys of any given relation. I'm going to support this with some more examples maybe that you can find in my part 2 of this video. So this particular video will explain primarily how to draw a dependency graph. So once again, welcoming you all for this fantastic kind of learning platform where you can easily learn with examples. Primarily, finding the candidate keys is the biggest task in this database design. But fortunately, we have this concept called as dependency graph, or alternatively, we can use sets as well in order to find the candidate keys very, very easily, which in turn helps you actually in order to normalize the relations in 2NF, 3NF, BCNF, etc. So this is an important concept which you might not find in most of the textbooks because they try to confuse you, and I'm going to make it very, very simple. So this particular YouTube channel will help you in order to understand this difficult task. So let me just move on to my PPT where we will see that so we have in order to find the candidate keys, we need to first draw the dependency graph. So let me just tell you how to do that. There are a set of steps or the algorithm which is required in order to carry out this process. So let me just show you that. The first step in the process of finding the candidate keys is nothing but draw the dependency graph for any given relation R with so many attributes like say A, B, C, and also a given set of FD. So what I've given here is a general kind of perspective. So later on, we will see more examples. Let's assume that we have an FD given as A arrow B. So where A is an attribute, B is another attribute of R. How to write the graph? So for each attribute in a given relation R, you first draw vertices. Supposing if I have 3 attributes given for R, I need to write 3 vertices, that is A, B, C. So in this case, let's assume that we have an FD like A arrow B. So what I write here is a directed edge from attribute A to attribute B. Supposing if you have another FD, let's say A arrow BC, then I draw 2 directed edges emanating from A and incident on B and C vertices. Supposing if I have another FD like A and B, then I would draw a directed edge from B as well as from A, which points to C, because we have A as well as B both to point to your vertex C. So whatever be the number of attributes you have on the left hand side, whatever the attributes you have on the right hand side, doesn't matter. All that you need to do is directed edges need to be drawn depending upon the FD. So if you have one attribute on either side, is one directed edge. And supposing if you have 2 on the right side, 2 vertices on the right side, then you have 2 edges. Similarly, if you have 2 what is on the left hand side. Again, you have two edges coming out of these two vertices. So this is the first step. So go through each and every FD in the given relation or given problem and try to complete drawing this. Before that, of course, you need to draw vertex corresponding to each attribute. Okay, now let's go for the step 2. What is step 2? Once you finish drawing the dependency graph, that means it shows that what are the dependencies among all these attributes as per the FDs given. Now step 2 actually will identify VNI group of attributes, which means that you need to identify the edges which have no incoming edges. That means vertices with no incoming edges. For example, supposing if I have A in this first case, A doesn't have any incoming edges, but B has an incoming edge. So I can say that VNI group will include vertex A, but not vertex B. So that's the concept of step 2, in which we try to identify only vertices with no incoming edges, which means indirectly, I mean, in other words, that we are trying to find all the vertices which appear only on left hand side. Remember, the attributes could appear only on left, only on right, or both the sides, left as well as right. So we are trying to actually find three types of vertices which may appear only on left, only on right, and then both the sides. Why? Because if we can find all the vertices which appear only on the left, that means with no incoming edges, that means VNI group, we can say that that's going to determine the dependence, because right hand side is a dependent, left hand side is a determinant. So we can easily say that that may be part of the key, definitely. So that we'll see how to ascertain whether it is part of the key or not. So step 3 is to find out all the vertices with only incoming edges. All the vertices with only incoming. For example, here, this is the only vertex with incoming. You should not have outgoing. That means vertices which appear only on the right side, because those are receiving edges. So this is nothing but all vertices which appear only on the right hand side. Now, for the moment, we need not worry about this both the sides, but as we progress, we will also try to find out another group called as both the sides, because most of the problem we may get these groups getting filled with some attributes or some vertices or otherwise. But there are some instances, very rare instances, where we could get no vertices in this group VNI, no vertices in this group called VOI, but all the vertices might go in both the sides. For example, in this case, I may have, something like this. When I have like this, that means, or let me just draw it with another edge to make it more clear. So in this case, what happens is that, do we have a set of vertices with no incoming edges? No. That means which appear only on the left? No. Do we have vertices which appear only on the right? No, because this has incoming, this also is incoming. This is outgoing, this is also outgoing. So what happens here is that both the A and B vertices will form under what is known as both the sides. Okay, they appear on the both the sides. So the corresponding FD is A arrow B, and then B arrow A. That means you can see here, my A does not appear just on the left, it appears left as well as on the right. In which case, we have both incoming. That means this is failed, this is also failed. No incoming, no, it is having incoming. You can see A is incoming, B also has incoming. That have only incoming? No. It has got an outgoing, and also A has got outgoing. So which means that this is failure, this also a failure. We can say that another set where I have vertices on both the sides. So that we will not worry now. So we will just assume that we will have some vertices here, some vertices here. So when I have a vertex on the left only, that means no incoming, only outgoing, which means that it is part of the candidate key, as I've already mentioned. Now, once we have this, then step 4, we can easily say that candidate key is a set of attributes, all attributes in VNI, because they appear on the left hand side. And if they appear only on the right, that means incoming, then that means that it will not be part of the candidate key. So this is gone. And not only that, once you find these attributes, we also need to find out that as no subset is already a candidate. So we should have a minimal set. So final checking also need to be done, that pick all the vertices here and then find its attribute closure. For example, if I have A only in this group, I need to find the attribute closure of this, and if it includes all the attributes of the relation, then I can say that it is a candidate key. Otherwise, it's not. We'll see that later, how to ascertain with more examples. So the way to write the dependency graph is very simple, that we need to follow. First, draw vertices corresponding to each attribute in given relation, and then draw directed edges for each and every FD and complete this and fill up these VNI, POI and both sides if necessary, and then we can find the candidate key very easily. So go through my part 2 of this video in order to find more examples, actual examples, so that you will be able to understand how to find the candidate keys of a given relation. Thank you very much for watching, and place your comments. Thank you.